Imagine an ancient people with a primitive number system like Roman numerals. Today on Inductica, we're going to examine how such a people could invent an algorithm for addition. But before answering that question, we're actually going to answer a more fundamental question, which is, what challenges would give rise to the need to have a system of addition to begin with? And finally, once a system of addition like this was produced, what process of reasoning steps would be required to prove that that system even works, that it even gets correct answers? The answers to all of these questions are coming up here on Inductica. In the last video, we covered the process of inventing Roman numerals. Our fictional hero, Rom, was able to compress units together. 5 ones was brought together into a V. 2 V's were brought together into an X, and 5 X's are brought together into the symbol L. This process condenses information and allows mankind to think about larger groups of things using the same amount of limited mental space. Now, before we proceed with addition, I want to point out the fact that I have not yet given a proof for the concept of zero. You may have noticed this, like other fundamental introductions to number include zero. The numbers are 0, 1, 2, 3, 4, 5. And then what about the negative numbers? I think it's pretty clear that there's no evidence for the negative numbers yet, because, I mean, if you think about it, first of all, like, what do negative numbers even mean? That's not an obvious, the answer to that question isn't obvious to begin with. But you probably immediately know, like, it has something to do with debt, and we haven't gone into that yet, so we don't have negative numbers. Okay, but why don't we have zero yet? Well, if you were to go to Rom and say, hey, why don't you write this symbol here whenever you have none of something? Rom would just look at you like you're an idiot, and he would say, well, why do I gotta keep track of stuff that ain't there? Now, eventually, there is a reason to keep track of stuff that ain't there, but we haven't seen that reason yet. This process of proof is observational. It is inductive. We do not come up with a new idea before there's evidence for it. By the way, this is a side note. This is part of why math classes are often so difficult for a lot of kind of rational people to understand, is a lot of people are evidence-oriented, and when new definitions are simply sprung on them without sufficient connection to reality, people legitimately balk at that and start thinking, like, is this really rational? I think that's a legitimate doubt that a lot of people have about mathematics when they're being taught traditionally. But part of my goal is to show how math can be taught using the observations. That is actually a side goal of this project. So we will never introduce a new concept until the observations that validate that concept are first presented. And so let's go forward to understand the observations that give rise to the need for addition. Motivation. The tribe of Babel is now a thriving town. They've become more and more wealthy by trading with nearby tribes, and they've gotten a pretty big town in a nice area between 2 rivers that's very fertile for their crops to grow. Rom has become very successful in his business. He's now moved into the town of Babel, but he makes regular trips to nearby city-states in order to trade with them. And currently he is on a trip to the distant land of Seshatet. This is my fictional version of ancient Egypt. I want to emphasize that this is a fiction, so I'm going to change the name. So Egypt is Seshatet. He's going to take a bunch of Babylonian goods to Seshatet, and he's going to sell them there because the people of Seshatet don't have access to a lot of the goods we have in the town of Babel. And so they're willing to pay a lot more for them. And Rom is able to make a profit for his efforts of bringing all that stuff over there. And once he stacks up on gold coins over in Seshatet, he's going to buy stuff in Seshatet and then do the same thing when he comes back to Babel, again for a profit. So let's say that he's just made it. He's just sold all of his goods from Babel, and he now has 210 and 4 coins. Okay, he has 210 and 4 coins. So again, that's the way that he would write 210 and 4 coins. Let's say he sells some additional goods and he makes an additional 310, 5, and 3 coins. Normally, he would just count the number of coins he has now. But he realizes, wait, I have the amount of coins I used to have written down on my clay tablet. I have it written down what I just made, the money I just made. So shouldn't there be some kind of way of figuring this out faster? That leads him to the following question. How can we quickly identify the sum of two groups whose quantities are known in Roman numerals? Investigation. First thing Rom does is he piles the symbols together. He takes the 2, 10, and 4, he takes the 3, 10, 5, and 3, and he just writes them all together. Now, remember, since each of these symbols is in one-to-one correspondence with some number of coins, he knows that this pile of symbols still represents the quantity of coins somehow. Remember, each 1 is in one-to-one correspondence with 1 coin. Each V is in one-to-one correspondence with 5 coins. Each X is in one-to-one correspondence with 10 coins. And so we are making reference to the basics of Roman numerals, which you can see the proof of in the cited video in the description. When he piles them together, it represents the number of coins, sure, but it's long. It's just this big pile of symbols that isn't easily understandable by the limited brain space that we have. So of course what he does, he's going to condense it. And he's going to condense it using the method of Roman numerals, the definition of the different symbols in Roman numerals. So the first thing he's going to do is he's going to order the symbols so that all the X's are first, then the 5s, then the 1s, and he's going to put periods between them so his mind doesn't become boggled. Again, the periods come between sets of 2. Then he's going to condense them. 5 X's are going to turn into an L. He notices he actually has 5 1s, so he's going to condense all of those into a V. Next, he notices that he has 2 V's. He's going to condense that into an X. Finally, Rom is able to see very quickly that he has 50, 10, and 2 coins. So he's used written numerals to speed this process of figuring out how many coins he has now. He doesn't need to count them. He's able to get to that final sum very quickly. Notice how the compression relationships of Roman numerals, the relationships between the symbols, that 5 tick marks is a V, that 2 V's is an X, these compression relationships, by writing them down, we're able to speed the process of calculation. The compression is not just a way of condensing the information, it's actually a shortcut for calculation also, or at least Rom has discovered that it can be used for that. And so he goes to some more places in the marketplace in Sechatet. He sells some more stuff and he makes more money. He just made 4, 10, 5, and 3. He just made that much more. So now he has his previous sum, which was 50, 10, and 2. And now he adds to that 4, 10, 5, and 3. Okay, so he's going to find out what this sum is. Now, after a while, I don't know this after the second time, but after a while, he's going to come up with a new symbol for adding instead of writing the word and. So he comes up with the addition symbol, let's say. And so first, he just piles all of these symbols together. Okay, then of course, we see out front that there are 1, 2, 3, 4, 5 X's. And so he's going to condense all of those into an L. Okay, so we get this. 5 1s is a V, so he's going to condense those. 2 V's is an X, and so he condenses it this way. He realizes at this point that L is kind of like V, only it's a V where each of the fingers is 10. So he decides that when he has 2 L's, think of it as 2 hands of 10 each. So that's really 10 10s. So he decides that he's going to make a number out of that now. He's going to make its own symbol. He's going to condense these 2 L's into a C. Okay, so not only has he come up with a method of addition, but because he's now dealing with larger quantities, he's actually come up with a new numeral, C, which is 10 X's, or 2 L's. Conclusion. To quickly identify the sum of two groups whose quantities are known in Roman numerals, write all of the numerals of both quantities together. Then compress those numerals into the smallest number of symbols possible. And lastly, as sort of a bonus conclusion, we have come up with a new symbol. 10 X's is C, or 2 L's is C. So our new list of symbols, to give all of the symbols, is now seen on the screen. What Rom has managed to do, he's able to use the writing of numerals to achieve something no one has ever achieved before, which is to quickly infer the total of two groups as once they are joined into one group, and to make that inference without actually counting. It has often been said that the invention of writing expands the mind. It allows us to put our thoughts on paper, and this allows us to simply have more thoughts. Instead of holding more thoughts in mind, you simply point your eyeballs at a different part of the paper, and now that thought will occur to you again. Well, Ram has not only used writing on a clay tablet, he's used writing not just to expand his mind, but to make the mind faster. The compression relationships between the different Roman numerals are actually used as basically a method of counting much faster. He's able to bypass counting and find out the quantity of two groups simply by piling the symbols together and then compressing them. So at this point in our epic story, we have accumulated quite a toolkit. The cultural hero Marduk of the Babel people invented quantitative comparison, putting things in one-to-one correspondence. That led to counting, putting the number words in one-to-one correspondence. That led further to numerals, putting units of a group in one-to-one correspondence with marks. That then led to a more efficient set of numerals, where sets of numerals can be placed in one-to-one correspondence with single marks, 10 units being put in one-to-one correspondence with an X. And now those compressed numerals, those Roman numerals, have facilitated adding, a way of grouping numbers together quickly and finding the total. But this is just the beginning. Every time mankind comes up with a new method, that gives rise to the ability to combine these methods together to invent even more powerful methods and to extend the reach of the mind even further. So if you'd like to see the next chapter in this epic mathematical journey, hit subscribe or watch the next video to find out how Ram is going to use his numerals to invent a method of subtraction. This video is part of a longer series dedicated to reproving the essential ideas of math and physics by showing an actual process of observation and reasoning steps scientists could have taken to prove these conclusions. Observational proofs, also known as inductive proofs, give us a deeper, reality-based understanding of these abstract ideas and demonstrate the proper method of scientific proof. This series starts with cavemen counting rocks and will continue all the way to the frontiers of quantum and relativistic phenomena. This epic story will proceed in a possible order of discovery, since science always progresses by reasoning about observations using what has been discovered earlier. To discover the long-term goal and the true power of this project, visit my channel page for more information. To see the playlist for this series or to see my channel, just click on the links on the screen. Finally, if you'd like more lectures like this, just go to patreon.com/Inductica. For just $5 a month, you gain access to the written, rigorous forms of these proofs, as well as my 34-hour lecture series, An Inductive Summary of Physics. I'll see you in the next video as this inductive journey continues.